What we're going to be talking about today is origins of an untamed landscape, the geology of the Big Sur coast. And every time I look to the south across Carmel Bay, or even the Carmel Valley, I'm struck by this wall that appears suddenly, and it's dark and forbidding, and mysterious. And part of me wants to explore that area, and part of me is glad I don't have to. That was probably the reaction, I suspect, of the early Spanish settlers in Monterey to this vast and largely inaccessible land to the south. They called it El País Grande del Sur, the big country of the south, or just shortened it to El Sur Grande, the big south. The term Sur was first used officially, as far as we know, by the US government in this area by the Coast Survey in 1851, who labeled the rock on which the lighthouse stands today Point Sur, a name that has remained with it. And in 1915, although a post office not that far away was established that bore the name of Big Sur. So we're going to today follow the following outline. We're going to talk about what the Big Sur coast is and why it's special. We'll talk about the foundation, the rocks that underlie it. We'll talk about its faults and the rise of Big Sur, which is a very important part of the story, and how it's been shaped by rainfall and waves. Next, we'll dive beneath the sea and look at the Big Sur coast underneath the water. And finally, we'll consider man versus mountain. Guess who wins? So what is the Big Sur coast and why is it a big deal? There is no standard definition for what it is. Some people take it all the way from the Carmel River down to San Simeon. In this presentation, I'm going to consider it as extending from Malpaso Canyon in the north, which is a very common northern boundary to it, down to Ragged Point in the south, south of which the mountains recede away from the sea. The coast is fronted by the Santa Lucia Range, a mountain range that occupies, it's part of the California Coast Ranges. And when I say untamed, what am I talking about? Well, as you look at this is really rugged, right down to the water level. The mountains are coming right out. If you go to other places like Point Lobos, it's a wild and beautiful place, but the coast next to it is pretty much flattened out. And this is true as you go up the peninsula from Monterey Bay. In fact, all the way to the border with Canada, there are very few places where the mountains come to the sea as they do at Big Sur. So that is in essence what the Big Sur is. It is just this wild, beautiful place and very, very rugged topography. Cone Peak, which is the second highest peak in the Santa Lucia Range, is nearly a mile high, and it is only 3 miles from the ocean, making it the steepest coastal gradient at that scale anywhere in the conterminous United States. That's Cone Peak off in the distance, very, very close to the shoreline. Robinson Jeffers, the poet, probably put it best as he usually did when he said, "Here from this mountain shore, headland beyond stormy headland, plunging like dolphins through the blue sea smoke." And while we're looking at this, I'll just note that the source of this is brockbradford.com. That website has some of the most spectacular photographs of the Big Sur coast I've seen anywhere. It's worth a visit. So let's begin with the rocks, the foundation. And if you've had a course in geology, one of the first things you learn is there are 3 kinds of rocks. There are igneous rocks, which form the cooling of a molten mass. Basalt forms at the Earth's surface, a very fine-grained rock, whereas granodiorite is another rock that we have here that forms from a cooling magma many miles below the Earth's surface. And we have sedimentary rocks, and these are produced by the accumulation of material at the Earth's surface, which then becomes cemented into rock. So mud and sand become sandstone, gravel becomes conglomerate, and organisms create limestone. And then metamorphic rock is any kind of rock that's changed in mineral composition or texture to another kind of rock due to heat and or pressure. And so we have these three very different kinds of rocks, which you don't have everywhere. I grew up and cut my geological teeth in Ohio. And in Ohio, the only rocks that crop out there are sedimentary rocks. They span an age of about 200 to 250 million years, and the individual rock units can be traced all across the state. Contrast this with what I'm going to show you next, which is going to be the inset map here at the same scale, showing the Big Sur at the same scale as this map of Ohio. And this is what you get. It is a real scramble. And in that small area, we have metamorphic rocks shown in tan. We have igneous rocks shown in rose and pinks. We have sedimentary rocks shown in yellow, capping these deposits. And we have one unit, the Franciscan complex, which consists of all three kinds of rocks, metamorphic, igneous, and sedimentary, all jumbled up together. So it is a very, very complex area. The best field geologist I've ever known once told me that if you can map in the California Coast Ranges, you can map geologically anywhere in the world. And I believe he's right. So we're going to start with the oldest rocks, the metamorphic rocks. These are part of a group called the Sur series. That's the formal geologic name for these rocks. And they're shown in the tan colors in the map to the right. I suspect everyone doing this has seen the Sur series metamorphic rocks, but like me, you probably didn't know what they were, but they're the rocks that underlie the Bixby Bridge. So anytime you go across the bridge, you look at these rather undistinguished rocks that form the base for the structure. The metamorphic rocks of the Big Sur are many. There is marble, which is metamorphosed limestone. Their metamorphosed shale can form a scaly rock called schist. And sandstone metamorphosed can create a very dense, hard rock called quartzite. But there are all sorts of other kinds of metamorphic rocks scrambled up in the Sur series as well. And to create these kinds of rocks requires immense heat and pressure, the kind I normally associate with the collision of continental crustal plates. The rocks, most of the rocks we have here are fairly young geologically, going back to probably most about 150 to 160 million years. But the Sur series, we don't know quite what the antiquity is. It's been interpreted by one person to be as old, the initial rocks as old as 1.75 billion years. And all I can say is that the kinds of collision that would be needed to create this kind of metamorphism, I don't see happening for the west coast of North America anytime in the past 300 to 400 million years. So we have two issues. One, the formation of the initial rock, and then the metamorphism, which completely changed it and pretty much wiped out information. So you lose a lot of information when you have metamorphism. A fossiliferous limestone becomes a marble, or a shale that can have all sorts of trace fossils or fossils in it, becomes a mica schist. And there is marble in the Big Sur at Piedra Blanca. And then the mica schist is also present pretty much throughout. These are some of the metamorphic rocks that are exposed just south of Cone Peak. And I'm guessing they're mica schist, although I can't really tell just from the photograph. But a whole bunch of really old, really changed rocks. And they can make their presence known even if they're not exposed along the coast. When you go to Pfeiffer Beach, or to Andrew Malera at the wintertime, particularly after a storm, you may see that the upper part of the beach is colored purple. And this color comes from tiny little garnets, that little mineral grains that are concentrated on the back beach and give it its color. And isotopic studies have shown that these originated in the schist that lies some miles inland. So what's happened is that schist is exposed, and the garnets, which are highly resistant to weathering and erosion, weather out. They're carried by the stream down to the beach, where they are ultimately concentrated by the waves. But by and large, the Sur series is a group of metamorphic rocks that have a story that really is lost in time. The igneous rocks are particularly prevalent in the northern part of the area. They are familiar rocks to us here because they form the foundation of the Monterey Peninsula and Point Lobos. And you can see that they occur in some fairly sizable bodies, but they're also broken up in smaller ones as well. And these are rocks that are composed of minerals that crystallize from a molten magma far below the surface of the Earth, and perhaps 5 to 10 miles or maybe even more. So how did these strange rocks form? Well, here we have to go to plate tectonics. And probably those of you who've seen my previous talks have probably could reproduce these yourselves. But basically the idea of plate tectonics is that the Earth has a solid lithosphere that sits on top of a plastic mantle that has convection in it and wells up with that convection at places like Oceanic Ridge, where new crust is formed, added to the lithosphere, and that spreads out and eventually moves across the sea somewhere until it collides with another plate. And these are the major plates of the Earth's crust. There are 12 of these, and some of them, like the Pacific Plate and the North American Plate, are very, very large. And the lithosphere consists of two types of the Earth's crust: oceanic crust and continental crust. Oceanic crust has heavy elements in it, and like iron, calcium, magnesium, and it's a dense rock, and it's typically dark. And the oceanic crust that's forming in Hawaii is a good example, kind of a classic example of oceanic crust that's actively forming today. Continental crust, on the other hand, is lighter, both in the elements it contains, like silicon, aluminum, potassium, and sodium, and it's also lighter in density and color, typically. So when you look at the Sierra Nevada, the crystalline rocks that are exposed there are good examples of continental crust. And the oceanic crust is formed on the ocean, mid-ocean ridges, where the mantle wells up to the surface and erupts in the form of undersea volcanoes, and then is carried off laterally until it runs into another plate. And typically this is a continental plate, and the oceanic ridge material, the oceanic plate, is more dense than the continental plate. So the continental plate kind of rides up over it in a process that geologists call subduction. So that's basically the mode of plate tectonics. One of the consequences of this is that water gets carried down into the deep earth by this process of subduction, and it gets to a point where the pressure is so great, it has to escape. And when it escapes into hot rocks on the side, then, and these would be Sur series rocks in this case, they melt and form a magma, a liquid magma. And when it cools, you have a big mass of granodiorite or other granitic rock sitting within the Sur series. This is just looking at the inset, which is going to be the whole screen in the next slide. And the point to note here is that we've got two kinds of contacts. The heavy dark lines are faults where the rock's been moved adjacent to one another. But if you look, there are lots of other places where the lines are not heavy. And these are places where the granite has pushed up into the metamorphic rocks. And that would produce a contact that would look something like this, very sharp, and just the contact between the unmelted but hot Sur series schist and a much younger granodiorite. And this all happened in the latter part of the age of the dinosaurs, the second part of the Cretaceous period, about 75 to 120 million years ago. And at that time, 80 million years ago, the plates off North America were quite different because North America was in direct contact with a giant plate called the Farallon plate. And the Farallon plate is moving, the crust is moving toward the North American plate and gets pushed under it, probably somewhere in northern Mexico, but nobody's really quite sure where all this happened. But the subduction occurred, and our igneous rocks, our granodiorites, were produced by this process of subduction. So that's the origin of the Big Sur granitic rock. Then we have what I think is the most interesting rock in the area, which is the Mesozoic Franciscan complex, shown here in green. And I'm going to focus on the lighthouse rock at Point Sur because you can pretty much get most of the story of what went on just from this rock. So what kind of rock is it out there that the lighthouse is built on? Well, the one description of it, written description I could find, is that says greenstone is Point Sur's most prevalent rock, but some altered gabbro crops out on the north side of the point, and some sandstone is scattered around. Greenstone, gabbro, what in the world are those? Well, we'll start with the gabbro. And gabbro is an igneous rock, did form from the cooling of the mass, and it is a rock that formed deep within the earth, underneath a volcano. And so gabbro forms in the depths down below erupting volcanic rocks, basaltic rocks. And so it has large crystals in it. And if these crystals get changed by later processes, they get altered to some other minerals. And so this is what they're talking about when they talk about altered gabbro. Greenstone, strange name for a rock, but that's what it's called. And it comes from basalt. And basalt forms at the same place as the same geographic location as gabbro, but it forms at the Earth's surface, whereas the gabbro is forming deep within the Earth. And it's produced where molten lava cools to the rock called basalt. Geologists utilize thin sections to study rocks and to identify minerals, a very powerful tool. And these are basically slices of the rock that are uniformly 0.03 of a millimeter thick. And a skilled geologist who uses the microscope a lot can immediately look at these thin sections using polarized light and identify the specific minerals within them. In many cases, it's really just at a glance. And then note that I'll be talking about crystals from time to time, but the mineral crystals don't have the clear-cut mineral shape, but they still are crystals. So basalt, that igneous rock that forms from cooling lava, under the microscope looks like this. And there are three minerals that are there that give its characteristics. They basically define it. Feldspar and olivine and pyroxene, and a basalt erupts at the Earth's surface. So it's the cooling of a liquid magma that can be as hot as 1,000 to 1,200 degrees centigrade, really hot, but at essentially atmospheric pressure. Now, if you take a basalt and later subject it to temperatures in about half that which they formed, but under immense pressures that you would get from 5 to 30 miles, say, below the Earth's surface, and those minerals are no longer stable under those conditions. So they convert to other minerals. And for basalt, those other minerals are two minerals called chlorite and epidote, and both of them have a greenish cast, which gives the rock its color and its name. Greenstone can be kind of green or not very green at all, but it still has the same minerals and still is got maybe a hint of green there. And then some sandstone is scattered around. So here we have in one rock, igneous, sedimentary, and metamorphic rocks, all in this one rock. And that is really amazing. And they tell an amazing, complex story. So what's their origin? How did these rocks form? Well, the Point Sur rock is part of the geologic unit that's called the Franciscan assemblage. And the Franciscan assemblage is a rock unit that exists quite widespread within the California coast ranges and well up into the coast ranges of Oregon. On the Big Sur coast, it's pretty much confined to the coastal front itself for reasons I'll show you a little bit later. And it contains some really weird rocks that puzzled geologists for years. Banded chert, back east, we would probably call this flint. It's essentially the same kind of rock, and but here it has a reddish color. It occurs in these bands, and typically in the Franciscan, those bands are really tightly contorted, bent, coupled. They're pillow basalts, big lumpy masses that occur on the basalt flows. And these are a really strange and very important feature. There's also the sandstone, which is a weird sandstone. It's called graywacky, which is kind of got a weird name as well as being weird itself. But a typical sandstone will show layering. It has lots of light colored grains, mostly quartz. But graywacky doesn't show that. Typically not much internal bedding and lots of dark grains. This is a thin section through what you might call a typical sandstone. And all the grains in this thin section are very light colored. Most of them are quartz. And you can see there's a distinct layering. There's a coarse layer that occurs in the upper third of the rock. And so it's made of mostly of quartz, and it shows stratification. But graywacky is just a hash, all kinds of grain sizes, and many of the fragments are quite angular. And if that gets bigger, that kind of a mess gets bigger, it becomes a rock geologists call breccia. And breccia is just a mass of broken up, angular pieces of rock that are all cemented together. The Franciscan also has some rather strange minerals like serpentinite. the California state rock. And in a few places, there's jade, particularly at Jade Beach, which is in the Big Sur area to the south. And as you look at those rocks on the shoreline, um, they are just a massive jumble. So that kind of jumble has been given a name by geologists, a melange, a mixture of unrelated material. And the melange can be really pretty big. In the 1960s, I had a project in Southern Oregon, and for a while, we had a helicopter at our disposal, and it was there for another purpose, but there were a few days when it could not be used for that purpose, and so it was available to me to use any way I wanted. We were already paid for it. And so I thought, well, this would be a good opportunity to map in these rocks that occurred offshore from Oregon. And some of these are a long way out, and there's probably nothing. I've never felt more lonely than sitting on a rock that might be a couple hundred meters across, 4 to 5 miles from the shoreline, and watching that helicopter disappear in the distance, bearing the only person in the world who knows where I am right now. And it was pretty exciting, and it was also pretty comforting to hear the chopper coming back for you. We actually totaled that chopper out doing this kind of work before the season was over, but that's another story. Well, geologists expect their rocks to have some continuity, that you can follow the beds and the layers over long distance, even where they're completely or much scrambled up as they are here in the Canadian Rockies. There still is continuity. Well, what I found out here was every one of these rocks was different from its neighbor. And these are just giant blocks in the melange, huge raisins in the pudding. So how, when, and where did these strange Franciscan rocks originate? And this is, I think, a really cool scientific detective story. And our first clue are the pillow basalts, because as we noted, pillow basalt comes from underwater eruption. And so where then would we look to find underwater eruptions? And the pillows form as magma, liquid magma, bursts out into the seawater and immediately solidifies into this rounded blob, but it's still molten on the inside, so it breaks out and will form another blob. So just a series of blobs that form on the seafloor. And they are indicative then of an underwater eruption. So where would that happen? Where might we find that? Well, the Hawaiian Islands certainly have underwater volcanism, but the Hawaiian Islands are volcanics that are occurring as the crust of the Pacific plate moves across a hot spot in the mantle. So as it moves, the volcano forms, and then it moves some more, and eventually another volcano forms. And this produces an island chain, but there's no way you could get the great swath of Franciscan rocks that we see in the coast ranges from this process. But there's another place that underwater volcanism exists, and that is on the mid-oceanic ridges, like the mid-Atlantic ridge shown here. These are really widespread, and basically they're sites of volcanism wherever you find them. And so you have at the surface this erupting basalt, and at depth you have gabbro. So there we've got two of our rock types that we find in that one rock at Point Sur. So this accounts then for both the altered basalt that we see and the gabbro. They both could come from a spreading ridge. And also we can get another material out there. This is from an active ridge off the coast of Washington photograph taken of Bambari, but notice all the sand. This is the rock material just breaking down and forming this sand, which is really dirty and made of all sorts of chunks. So there is the source of our greywacke. So this then explains the other rock that we have, all in the same place, all coming from underwater volcanism, probably around a mid-oceanic ridge. But where was that mid-oceanic ridge? Well, here we go to our second clue, which is the banded chert. And the banded chert was shown with the development of the electron microscope to be composed of tiny little animals called radiolarians. And these are single-celled animals that have glass shells. And the ones that were found in the Franciscan were of a type that you would find in tropical or semi-tropical waters. And today, where we get concentrations of radiolarians on the seafloor is near the equator. So we can focus our search then, looking for some place where a mid-oceanic ridge crosses an equator. And the age of the radiolarians is consistent with them being about 160 million years old. But that's 4,000 to 5,000 miles from the North American continent, or what will become the North American continent. And is that even remotely possible? Well, an estimate of the spreading rate of the Farallon plate was 5.3 inches a year, which over a million years would be about 85 miles, or over 60 million years, 5,000 miles. So the answer is yes, this is entirely possible. So I think there's a good chance that the original basalt of this rock crystallized on an oceanic ridge somewhere in the order of 150, 160 million years ago. And that ridge was 4,000 to 5,000 miles to the southwest near the equator. So that rock has moved a long way. But how, when, and where was it converted to greenstone? Well, the seamounts that form from volcanism near the ridge are carried by the plate across the ocean and eventually wind up colliding with the North American continent. Probably looking something like this image of the continental slope of Costa Rica, the continental margin, and you can see the subducting oceanic floor carrying seamounts, which are volcanic rocks, into and crushing them against and under the continent. So I think that's what was going on, that the seamounts were forming on the ridge or near the ridge, they were carried across and then subducted under the North American continental plate. And that subduction really messes things up, especially as these seamounts would be coming in. And if the seamount material, the basaltic material, gets carried down to deep pressures, then it forms the greenstone. So that's a way of getting our greenstone. And in fact, if you get it far deeper and with enough water, you'll create serpentinite and jade. And the rest of it just gets all completely mashed up as this oceanic material is crushed against the edge of the continent. So I think we could say that our Point Sur rock is part of an ancient submarine volcano that was converted to greenstone and altered gabbro during the process of subduction. And the age has, for that subduction and metamorphism, is considered to be about 77 to 87 million years ago. Well, this overlaps the time of formation of the granodiorite and the granitic rocks in the Big Sur area. So while that subduction was going on at the same time, that was when water was being extruded from the oceanic crustal material and getting into the continental material and melting it, creating the magma that would be our igneous rocks in the Big Sur. And all of this is happening probably well to the south in what today would be northern Mexico. And so that raises the question of how did the rocks get here? And those of you who saw the talk last week saw this as well, that behind and to the south of the Farallon Plate was the Pacific Plate, and it's moving to the north. This whole system is moving to the north. And as it moves, the Pacific Plate starts to encroach on the North American Plate. So about 35 million years ago, it still hadn't collided with North America, but it was getting close. By the time we get to 25 million years ago, that collision had likely taken place, and the other plate that had been there, the Farallon Plate, was broken in two and became the Juan de Fuca Plate and the Cocos Plate to the south. And with that process of the Pacific Plate moving north, chunks of rock were attached to it, broke off, got attached to it, and got carried up by the Pacific Plate as it moved to the north. And so that's how these rocks came from where they were initially metamorphosed up to their present location today. And that happens because Big Sur has its faults. Lots of them. This map, again, the faults are the heavy lines, and there are many faults, but I want to focus just on two really large and I think very important faults in this story. One of them is called the San Gregorio Fault, and the other the Sur Fault. And both of these faults have extensions to the south that are other faults, like the Hosgri Fault for San Gregorio and the Nacimiento Fault for the Sur. And sometimes you'll see the name just reflect the San Gregorio Hosgri Fault is the term that's given to the fault, or Sur Nacimiento. But up here, we can call them just the San Gregorio and the Sur faults. And these are very different faults. The Sur fault is a reverse or thrust fault, meaning that the rocks are pushed over themselves along that fault line. And this results from compression. It's a way of shortening the material. And some faults can be very gently inclined, and there are places where the overthrust strata has been moved up to hundreds of kilometers, so they can transport rocks a very, very long way. Well, our granitic magma that was going to produce the granodiorites and the other igneous rocks in the Sur series formed 5 to 10 miles below the surface. And they were carried up to the surface by the thrusting motion of the Sur Nacimiento Fault. So that's how they got up to the surface. But when? When did this happen? Well, probably the best evidence comes from Point Lobos, because there we have a submarine canyon that's cut into granodiorite. And that means the granodiorite was exposed at the Earth's surface by some 50 to 55 million years ago. But the granodiorite is 80 million years old. So sometime in that interval is when the Sur Fault was active. And so its displacement occurred probably 60 to 70 million years ago. So it's a very, very old fault, and not likely to cause earthquakes today, although it is a zone of weakness, and any zone of weakness can create a significant earthquake. The San Gregorio Fault, on the other hand, is a very different fault, and it is active today. In fact, less than a month ago, there was a little earthquake on the San Gregorio Fault, just a few miles offshore from the Monterey Peninsula. I'm sure none of you felt it. It occurred at 1:32 in the morning, and it was only a 1.9 earthquake. My son, who keeps a seismometer in the garage, did record it. It did happen. So the San Gregorio fault is a transverse fault. It's a strike slip fault where one side moves sideways by along the other side. And it's part of the system of the San Andreas fault system that is a series of faults that are made by the interaction of the North American plate and the Pacific plate. And this fault can generate some significant earthquakes. October 22nd, 1926, there were two earthquakes an hour apart, each one a 6.1. And there wasn't much damage in Monterey. Santa Cruz had more damage, probably because it was more developed at the time, and Monterey was not particularly developed then. But those faults, if that happened this afternoon, there would be, I think, sizable damage on the Monterey Peninsula. And if the San Gregorio and the Hosgre fault merged and all moved together at the same time, it could create an earthquake as large as the 1906 earthquake. But the chances of this happening are infinitesimally small, thank goodness. Now, the San Gregorio fault has another bit of motion to it, and that is it is rising up on one side. So it's not just sliding sideways, but it's also moving up one side relative to the other. And that brings us to the rise of Big Sur. So San Gregorio fault is part of the whole fault system that we've talked about. Those of you who saw the talk last week have seen these slides. When you get two plates moving against one another, it's like putting your hands on a tablecloth, moving one toward you and one away from you, and getting a wrinkled tablecloth. And the wrinkles are big in this vast setting. And part of them are the Santa Lucia Range, which is rising up at this time. And part of this is due to the San Gregorio fault, because the amount of upward movement on the San Gregorio increases to the south. And part of this may be due to the fact that the fault bends in something that has been called by geologists the Big Sur bend. But it's this lower white area shown here, but it deviates from the track of the San Gregorio and to the south, the Hosgre fault. And this may be an important factor in the creation of the uplift. Strikes of faults are usually fairly straight, but they can have bends. And when they have bends, there are consequences, because where the bend is to the right, as you look down on it, the direction that it's moving, a basin opens up. You make a hole because you're pulling the material away. But on the other side, where it is colliding, then you get uplift and range development just due to this process of a bend in the strike slip fault. And so the Big Sur bend it's been suggested that that bend was enough to create uplift of the Sur area. And there is uplift, and it's significant. 600, more than 600 meters along the coast, up to 900. It is an area that is actively moving upward. And it may well be that part of that, or much of it, is due to that bend in the San Gregorio fault. The rate of land rise is estimated to be about 700 meters in a million years, which is not much at any one time, but over a long period of time is really quite significant. And superimposed on that in the last million years are the fluctuations of sea level that are caused by the alternating glacial and interglacial episodes, because the ice that's locked up during a glacial episode comes the from the sea, and so that water is pulled out and put on land, and sea level falls. So during these blue intervals shown here, which are the glacial intervals, you can see that the sea level has fallen. Then the ice melts and sea level returns to a high stand, which is where it is today. Well, in this process, waves will cut a platform, and then sea level falls, leaving that platform high and dry. And then sea level comes back, but it doesn't reach that previous point because there has been uplift. The land has moved upward and carried that old wave cut platform up above it. And you can see that pretty clearly at Point Lobos. This is the lowest raised terrace that's exposed at Whalers Cove at Point Lobos. And this is the lowest raised terrace down on the Big Sur coast. And look how much higher that is. That's how much the coast has gone up in the same amount of time in the Big Sur compared to Point Lobos to the north. And once it's raised, then it is sculpted by rainfall and by waves. Big Sur is a really wet coast. There's a lot of rain there, and the reason is that the winds coming off the Pacific, the atmosphere, the air they're carrying is full of water, it's saturated. And as it rises, when it meets the coast, it cools. And in that cooling process, the colder air can't retain the same amount of moisture that warmer air does. So it comes out, and it comes out in the form of rain. So as the winds blow up the side of the mountains, the seaward side of the mountains, that warm, moist air drops its moisture, its water content, and you get lots of rain. And then as you get back on the inland, it's dry and somewhat almost semi-arid. So Big Sur, in terms of average annual rainfall, is probably the highest area in the California central coast for sure. And the rainfall there can be pretty excessive. In 1941, they had 160 inches of rain. I can't even imagine what that would be like. And all of that rain sustains and promotes the growth of vegetation. So the hills turn beautiful and verdant with lots of wildflowers. But then as we go into the dry season, that dries out and becomes fuel. And so we get fires along this part of the coast. And the fires burn off the vegetation, and then that exposes the bare rock to processes of erosion, and it starts falling down, crumbling. And if you get a heavy rainfall, you get lots of water moving down, carrying lots of sediment cutting into the slopes. Much rain wears the marble. These were lines penned by William Shakespeare in his Henry VI, Part 3, and they could apply to the Big Sur coast. As far as I know, William Shakespeare never saw the Big Sur coast, but I don't know, maybe somebody sent him a postcard. Moving along, we'll go to the waves, because that's another source of erosion. And if you look at this bathymetric map or chart, along near the coast, notice how where the red lines are, the contours are closely spaced. That means it's a much steeper gradient there than it is further offshore. So the water is deep, really up to the shoreline. So the Pacific swell, the big waves coming across the Pacific, don't really lose any or very much energy as they go across that deep water bottom. And the result is they can pile into the coast with full force. So they then cut into the rocks. The result is just a very precipitous coastal slope. And it doesn't end at the shoreline. part of Big Sur that's unseen is really fascinating. Below the sea, there are two submarine canyons. There's a seamount out there. And the submarine canyons are kind of strange because most canyons come up and will head up into a single source. And from that source, you get turbidity currents that cut the gullies and eventually cut a canyon. Well, here you've got all of these gullies. There's no central source. And I suspect that's because we don't have a really large river coming into the coast anywhere along here, but instead we're getting lots of eroded material carried out onto and near the shelf where it cascades in turbidity currents down these gullies. And that's what's forming the gullies that eventually emerge to a canyon. There are just lots of questions out here. What is Davidson Seamount? What is forming these canyons? Why do we have this bend up near the top and Monterey Canyon? And we've got something here that looking at it, this linear feature that comes across here, looks for all the world like we've got a fault out there. And Partington Canyon is offset by that fault. But the sense of offset, the sense of movement is exactly opposite to all the other big faults in the area. That doesn't make any sense. I would love to come back in 50 to 100 years to see if we have answers to some of these questions, but it's absolutely fascinating out in the offshore areas. Well, Big Sur is a beautiful coast, and all it needs is a road. And we do indeed have a road. Highway 1 comes up the coast. And this takes us to our final topic, man versus mountain. This happens all the time with that road. It's rated by many sources as one of the most beautiful coastal highways in the world, but it probably is also one of the most costly to retain. And it is just, it's precarious. It was built, work started on it in 1919. And much of the labor that was provided was by convicts. There were camps that were built along the coast, and the convicts who were in these camps worked on the road. They were paid for their efforts starting in 1921. They got the grand sum of $2.10 a day. But out of that had to come the expenses for their meals, their clothing, any medical expenses, their tools, transportation to and from work sites, and the salary of the guards who watched over them. There was also posted a $200 reward for the return of any convict who escaped and then was captured. And I'm just guessing that you did not want to be a convict with an unsuccessful escape attempt, that the reward money came out of all the rest of the convicts. It would not lead to your being voted the most popular convict on campus. But they did create a road, and on September 18th, 1934, automobiles made the first drive from San Simeon to Carmel. The road wasn't paved at the time, and many of the bridges weren't completed, which meant they had to cross timber structures that were sort of makeshift structures to get the vehicles across. It was probably a very exciting trip, and it can still be a very exciting trip today. The fact that we have these steep slopes, the rocks that are all broken up, and the heavy rainfalls that we have means that there is a lot of instability along this part of the coast. And road closures occur a lot. In the time since the road first opened in 1937, there have been 55 closures, which if you average them out, it's 2 every 3 years. And during that season of really heavy rainfall in 1941, the state seriously considered closing the road. Now, I don't know how many of you, like me, were taken in by the story in the Monterey County Weekly on April 1st about permanent closure of Highway 1, but I was, and I went through the article looking for material I could use in this talk. Fortunately, I didn't find any because it turned out that was their April Fool's edition. And so the state is not planning to close Highway 1 permanently, although they really did in 1941 with that heavy rainfall, consider just abandoning the road. Lots of things happened to the road. This is the Mud Creek slide 2017. About a quarter mile of the road was covered by this giant slide, which was about a million cubic feet of material. And one of the things that I find really interesting is notice there's a trail over here on the right-hand side that goes up some buildings. And they are built on an old landslide, which may be one of the safer places along the coast because all of those stresses that initially were there are gone. Then I look at that steep hillside behind them, and I decided, yeah, I don't think I want to invest in that property. The most recent closure occurred at the end of January in Rat Creek, and this one was caused by a heavy rainfall coming down on an area that had been denuded by fire, and so the water, there was nothing to retain the soil, so it fluidized and became essentially a river of flowing mud that as it came down had immense force, and when it hit the road, it overwhelmed the drainage system and just totally took the road out. But Caltrans has it open again today and has repaired it. So wait till next time. I sort of think that if the Almighty had wanted a road to be built along the Big Sur coast, she would have made it a lot flatter. But then it wouldn't be the Big Sur coast. I have to admit that every time I'm down on the Big Sur coast, I have a sense of disquiet. And I think it's probably due to the fact that I've spent much of my career performing autopsies on older rocks that are tens or hundreds of millions of years old, one piece even more than 1 million years old. And so I'm dealing with rocks that are no longer active and trying to reconstruct how and why and where they formed. Sort of a sense of relief when I cross the entrance coming back to Point Lobos and know that I am back on the safe land of old rocks, old geology. And with that, I will close.